For chapter 4, 4.1 lesson, we probably need to backtrack and do a little bit of a review about H plus molarity, that's brackets, and pH. So for real simple terms, for instance, if the molarity of H plus was 1 times 10 to the negative 3, which is this, then the pH, of course, is negative log of that value. So this is 1 times 10 to the negative 3. And what we're saying with this is, what is the number that will get you as an exponent on 10 will get you that number? What number on 10 as an exponent will get you that? And obviously the answer is negative 3, except that people are so bad with negative numbers that we're going to take off the negative. We're going to say negative of whatever that other answer was just there, which was negative 3. So we're going to take the negative of that and get positive 3 as the pH, because it's easier to teach people that the basic range is from 14 to 7 and the acidic range is from 7 to 0 than it is to teach them negative numbers. And if we mess up pH a lot, we're going to get a lot of dead fish and really weird swimming pools. So then also we can do the opposite, and we can go from pH back to H plus molarity. And boy, is this all going to come up quite a lot. If we told you the pH is 3, then what you can do, and I would grab a calculator and try this, is say inverse log or second log or shift log negative 3, and it should give you 0.001 or 1 times 10 to the negative 3. I will point out that I said inverse log of negative 3 because remember we took off the negative when we did this? Well, let's put it back on first, because otherwise you're going to get 1,000. So it's going to be inverse log, second log, shift log of negative 3, and it should return you back from pH, out of pH into the molarity, and you should get 0.001. Now, all our problems are going to be done at 25 degrees Celsius, unless they say very explicitly otherwise, in which case we know the constant for water is 1 times 10 to the negative 14, the Kw. So we know that the H plus molarity times the OH minus molarity must vary in proportion so that this is the constant for water. So if you know this one, you can divide and get that one, and vice versa. And therefore, since this gives us a this would give us a pH and this pOH, the pH and the pOH must add to 14. So notice that what we get is water breaks up and is in equilibrium with H plus and OH minus. And so you can think of this a bit as a KSP. I know that's not a solid, but it also isn't aqueous, which is another point to make. Water is not aqueous in water. There is no molarity of water in water. It is water. Now, neutral conditions, the whole entire point is that the only presence of H plus and OH minus in the water is from the dissociation of water. And so when that happens, we get equal amounts. Now, remember that water is not aqueous in water. There is no molarity for water. So this is a bit like a solid in a KSP expression. It doesn't figure into the K math. And so we have equal amounts of this and that because they were made in a 1-to-1 proportion. Therefore, the K math is the molarity of this times the molarity of that to the power of the number in front, but that was both 1, and they are the same number. So we essentially get Kw equals x squared. So these are each the value of the square root of that. So they are both this number. And they are made, they are used up in direct proportion. If you dump in some chemical, they go up and down in direct proportion. If this doubles, this goes to half and so forth. If this is multiplied by 100 and goes up 2 decimal points, this is divided by 100 and goes down by 2 decimal points. So if we take the negative log of the H plus, we get POH. If we take the negative log of OH minus, we get POH. And since these were both the same number, when we do that, we get the answer is 7 for both of these. So at neutral conditions, pH is 7, POH is 7, and that adds to 14, and that's not at all a coincidence that it comes from this, because remember, we took the negative off back here. And so if this goes up by 2, that goes down by 2, because that's a reflection of the 2 decimal points I was mentioning before, because this is a logarithmic scale. If you don't quite know what I mean there, ask your teacher, but this will add to that. It will add to that at 25 degrees Celsius. These two will multiply to that at 25 degrees Celsius. On B, they have an estimating problem, which they really do think you can do for the multiple choice questions. They want to know if you can identify a pH range, not an exact amount, but at least a range. So if we have a strong acid, KOH, and by the way, they really do think you know your strong acids and bases. So get a list and memorize it. Here's a strong base, by which I mean all the OHs will come off. They will all come off into water and become OH minus. So if the molarity of the KOH is this, then the molarity of the OH minus is this. And for the purposes of pH, potassium doesn't matter because potassium has about 0 ability to grab any OH minuses back out of water. That's why it's a strong base. It is terrible at holding on to OH minus in water. So all these come off and this won't grab any back, at least not enough to matter to anyone I've ever heard of. So the molarity of the OH minus is also this amount. So what's the pH in this case? Well, the OH minus molarity is this. Now, somebody's going to say, well, it's this plus the amount from water. Oh, okay, but you know what? By the time you get done adding this to that, it'll not even matter when you get done with the rounding. By the time you round off, you literally won't tell the difference. And I mean won't tell the difference. So let's just forget it. Technically speaking, for all you math nerds out there, yeah, I know, you're right. And the math classes said you can't disregard a number just because it's small, and we'll force you to add on the amount. Yeah, I know it's this molarity plus that molarity, but you know what? In real life, that's too small to matter. Forget it. So we're just going to say the molarity of the OH minus is this. So how would I know what the pH is? Well, I know what I can get what the pOH is, at least sort of, because this slots in between these two numbers. If you don't know what I mean, hit pause and have a think. This number is between these two numbers. This pOH would be 4. This pOH would be 3. So the pOH is between 3 and 4, and therefore, since the pH and the pOH have to add to 14, then it's between the numbers that make that add up. This adds to 14 and that adds to 14. So 14 minus this one gives me that one. 14 minus that one gives me that one. And the pH is between 10 and 11. And then if you do the inverse log, you can say that the H plus molarity then is between 10 to the negative 10 and 10 to the negative 11. Now, a fundamental part of this is that the pH scale is basic above 7 and acidic below 7. And I know it seems like the opposite way, and I sure expected it to be the opposite when I came across it, but here's the idea of the math. Here is very little amount of H plus. Bigger is less negative, smaller is more negative. Hit pause and have a think about that if you need to. This number is much smaller than that number. So this is very little H plus. This is quite a lot H plus by our standards at least. This stuff I wouldn't put in your eye, that's for sure. A pH of 1, yikes. That's like lemon juice or something. Now, as this amount of H plus molarity decreases, when we take the negative of the log, we end up with the positive value of this. And so the less H plus there is, the greater the pH number becomes. If we have very little, 1e negative 14, what's the pH of that? 14. But I said very little H plus, so that's very unacid. It's very basic. As the H plus molarity increases, I could get out to say this, and that's quite a lot of H plus molarity. But when I take the negative log, I get the value of 1, and that's very acidic, but it looks very small on the pH scale because 1 looks like it's small. Another point I'd like to make is how a logarithmic scale works, and this is going to come into some of these titration curves we're going to see, that it's easy to push a system off the neutral pH, and the farther you go, the harder it gets. Because to go from 7 to 8 in the pH scale, you need to change by a certain amount. You need to change by 1 decimal point. And every number after that is a factor of 10 compared to the last one. So to go from 8 to 9, you have to go 10 times the distance you had to go from 7 to 8. To go from 9 to 10, you have to go 10 times the distance you had to go from 8 to 9. And so the problem just gets worse and worse and worse, and shifting in and out of extreme pHs is a lot harder. You have to use a lot more chemical to do it. So remember that when we talk about these titration curves that have steep inclines in the middle at pH 7 and then tend to flatten out toward the extreme ends of the pH scale. On example 2, they want us to compare pH 3 and pH 6. So what would the molarities of that be? Well, pH 3 would be inverse log of that number. Inverse log of -3. So you would get 1 times 10 to the -3 is the molarity that corresponds to this, and 1 times 10 to the -6 is the molarity that corresponds to that. And these are different by 3 decimal points, which means that this is 1,000 times bigger than that one. And for figuring the OH minus molarity, of course, we can figure that out by remembering that these two have to multiply to be kW. So what I can do is take kW and divide by that, and I'll get that. And we should learn to do that in our minds because it's just 1 divided by 1. So of course this part is 1. And then we just add and subtract the exponents. So we're saying -3 plus something equals -14, and the answer is -11. And in that way also we get this, and then this number is bigger than that one. So the ratio is 1 on the top, 1,000 on the bottom. On C, we want to talk about, well, what if the water was at 100 degrees Celsius? And I'm not sure how much this applies to the test, but it is an interesting point, and it might drive the math home more. So the kW is this. Okay, sure it is. Now, the kW is that, therefore, the value of this and this, which I know are equal at neutral amounts, are x, so to speak, x squared. And so the value of each of those is the square root of this, which turns out to be that. And so the pH, and I said we were talking about a neutral system, the pH of a neutral system then is 6.14, and the pOH, of course, is the same number because we're taking negative log of the same value. And so at 100 C, the pH dividing line is 6.14, and less than that is acidic, and greater than that, not 7, but 6.14 is basic. And of course, they have to then add up to the negative log of the kW, and the kW is not 1e negative 14, it's this. So they have to add up to that. On D, what are all our standard little questions here about pH systems? Well, the first one doesn't change, and the reason is because we dosed it with a decent amount of strong base, remember, back from the example 1. And so this amount is so much more than would be created by water even at 100 C that adding in the amount from 100 C doesn't matter, and I'm just going to say forget it. It's not enough to worry about. It won't change my answer. So the OH minus molarity at the beginning is unchanged to the point where it's just not worth bothering with. So I'm going to say that it's the same thing as the first time. So the negative log of that number, of course, is the answer we got last time, and that's the pOH. However, it's in equilibrium with H plus in a different kind of system because now I don't subtract out of 14 to get pH. I subtract out of 12.29, and I get a different pH because remember, we didn't dose it with an H plus type chemical. We dosed it with an OH minus type chemical. And so the pH is going to change because it's not subtracted out of 14. And then the H plus would be the the inverse log of the negative pH. So it's going to be inverse log or shift log or second log or 10 to the power of negative that, notice, and we will get a molarity for the H plus concentration in this 100 degree system.